Hi, it's Clark on Temptress. A bit ago, I put out a request. Hey, what would you like to see videos on? Someone said how to wire a boat. That's a good idea. I've gone kind of deep in how wiring works, how fuses should be chosen. That's all in a good playlist, but let's just do a fairly simple, really straightforward wiring of a boat. I'm also going to show you how I do grounding in my wiring, which is completely different than any other boat I've ever seen. In this video, we're going to go over what's on this desk. I'm sure it looks like a mess right now, but when you go over it wire by wire, bit by bit, it'll make perfect sense and it will illustrate a lot of important features in how to wire a boat. This is the same for wiring a camper, anything DC. So, this could be useful for a lot of people. Let's take a look. But before we take a look, I want to draw you a picture. Almost every boat I've ever seen, certainly I'd say every boat I've ever seen, they run the positive to a distribution panel and they run the negative to the same distribution panel. From that distribution panel, they run wires to every device that needs it, both positive and negative. Every light, every sub-circuit, your refrigeration, everything gets its own ground wire that goes needlessly too far. And, since copper's expensive, it's all the smallest wire that will do the job or somewhere in that order. Well, resistance is not your friend when you're doing 12-volt systems. It's particularly nasty with the low 12-volt system. Just a little bit of resistance causes a voltage drop. There's always resistance in everything. So you want to minimize it. You get resistance when you use wire that's small. You get resistance when you use terminals at the end, that you crimp on, and bus bars and connectors, and any union causes a little more resistance. So if we can minimize those in the whole circuit, and the circuit is from the source, the battery's negative, out to the device, through whatever fuses and distribution and switching, and back to the battery. That's the full path, and if we can minimize its length or maximize the size of the wire, well, there's a savings. Since we're only at 12 volts, like if you have 1 volt of voltage drop, that's like almost 10%, and that's a problem. The worst offenders I've ever seen to this, there's a French boat. Okay, French boats all seem to be wired strangely as a group, but this one in particular, from the battery compartment, the hot wire came out, it went through a fuse, it went through a battery switch, it went through a bunch of other buses and distributions and stuff, and then it went off to where it was supposed to go. On the negative side, it also went through a fuse. Well, it's a circuit. You don't need to fuse both sides. Then it went through a battery switch. Well, if you have a switch to shut off the positive, you've shut off the negative because there's no circuit. Then it had the same distribution buses and all of that. The short of it was, why I was called to look into this boat was the fridge just did not perform very well. And while the fridge was operating, even though the batteries were up to full voltage, the fridge was seeing like 9 volts. Just all of this voltage drop and generally undersized wires from switches and stuff. Completely unnecessary. Now, if you go back to the way I described it, where you just have the negatives go to the distribution panel and then out again, the downside there is that's probably not the quickest route, but also when you come from the distribution out to the actual devices, you're going to use as small of a wire as is appropriate. But you don't want to have like 2-gauge wire everywhere. First off, it's expensive. And second off, that's just a lot of weight and a lot of effort pulling. So this is what I do on Temptress. This is what I do if I set up a boat. And if your boat's going to get rewired, really think about this. If your boat's just, you're just adding to it like we do, and that's what I did on Temptress. I probably still have some ground wires that take the whole old route because they've just never been a problem. But anything I have to rewire goes onto this. So here's what it is. Okay, so here's my very bad drawing of a boat. Made her a counter stern because that's what Temptress is. My batteries are in the middle. And my distribution panel is here with all of its switches. So the positive wire comes up with a big wire to the distribution. There's a fuse here. It has circuit breakers here that break down to the smaller circuits, because when you go to smaller wires, you have to go to smaller maximum current, and we control the maximum current with either a fuse or a circuit breaker. And then they go out to wherever, to all the devices. But from the negative point of view, I do something a little odd. I use a great big wire. I think the first length of it is like 1 gauge. It runs forward to a bus bar about here, and then I've got a smaller wire, I think it's like 6 gauge, that goes up near the bow and another distribution. From here, it comes back with some very big wire to a distribution, a bus, and then from there on back to another one kind of in the steering compartment. Now, for all my devices, let's say I have a light here over my saloon. The positive for the light has to go down the wiring track, and there's a place here where it can go under the floor and come up to here, and then of course it goes back to the battery. But the negative just goes down there to the nearest bus bar. So the path from the negative side is big wire, appropriately sized wire, but only feet long, and then the necessary long wire to do the other side. Had I not done that, this long route would be multiplied by 2 as the ground goes back, and also the wire would be smaller. My fridge compressor is right here. Now, it has a fuse on the panel, so I can shut it off, and it's got there's a big wire going up to here, and then a big-ish wire that comes to there. Most all of the power in your boat is going to be consumed in the refrigerator. So any voltage drop going to the refrigerator, like if you're losing 10%, you're like losing 10% right out of your batteries. You want to minimize that. That's where you want to do your copper investment. Okay, so that happens. But now for the negative side, the wire just goes right to here. And, it's a pretty big wire. I think it's like 6 gauge from the refrigeration area to this distribution. Then from there, it's a 2 gauge wire to the batteries, and that works out. So this guy is normally running alone. All night he's running alone. There's no lights on or anything, and nothing else is sharing this path. So he's just got lots and lots of copper, virtually no voltage drop on the negative side. So if there are other loads running, well, the fans are running and the lights are running. That's not a lot of power, and they're still on very big wires, so it's not a problem. And I didn't have to spend the money on the copper to run great big everywhere. And of course, if just the fan's running, he's got milliamps running down like 2 gauge wire, so not even an issue there. Okay, keep that in mind. It's just a way to go. I've set up a little lab here. I'm going to turn the battery on. This is a battery with a switch on it. So it's on now. And this is what I have set up. Don't go by the gauges of wire I'm actually using. I chose gauges based on what I had laying around. But big is big, small is small, that kind of thing. But the why is what's important. First off, since I'm messing with batteries, off goes the watch. You don't want wedding rings on or anything when you're working with DC in particular. I think the first thing to talk about is the overriding rule for safety. We need to control the current that can go through anything, any piece of wire in particular. So that's fusing. I have a whole video on fuses in the playlist for the masterclass in electricity. This will probably become part of that series. But we need a way of controlling the current that can go through the circuit such that the wires can't get into trouble. Fuses are not there to protect components. Fuses are there to protect your boat from a wire becoming a heater. Okay? There's nothing you can do to protect the components, and components for the most part will just internally burn out if something really bad happened. It's the wire that can get into trouble. Now, you really only have to break the circuit with a fuse in one place in the circuit. By that I mean you only have to fuse one side, the negative or the positive. Without the positive side available to the battery, the negative is absolutely benign, and vice versa have you done it the other way. I personally always say you should put your fusing on the positive side, and that's for one reason. Your engine block is going to be grounded to the battery on the negative side in a way that you really don't want to fuse because it has to be such a huge fuse. The starter on a diesel is like 800 amps. So you don't want to fuse that. And the engine block is this great big piece of steel or aluminum, but conductive. So there's a big thing there that if a wire got loose and touched it, bad things would happen. So if we protect the positive wires, think of one of them hitting the engine block, their current would start going really high, the fuse would blow, no problem. Where if we protected the negative side, all the wires that could have fallen off, a little bitty wire could fall off. Now it's going to be asked to pass 800 amps before the fuse blows. Well, a 12 gauge wire will start a fire before it gets to 800 amps. We actually have current control in the lithium battery itself. All BMSs have a way of controlling current, but don't count on them to save your life. It's electronics, it's active. They're done with something called MOSFETs, the switching. And when MOSFETs fail, sometimes they fail on, which would mean I can't turn off no matter what I'm seeing. So as soon as you leave the battery, you want to go through a fuse big enough to protect the wires that are downstream of that, immediately downstream of that. And in this case, I have a 200 amp fuse. It's inside this little case. I've also mounted them in such a way that one side of the fuse mounts right to the terminal on the battery. There's still the protection you need to keep it from like spitting molten metal, but honestly, these don't seem to blow in a bad way at 12 volts. And then the one wire leaving that. So technically this wire is unprotected. You just have to draw the line somewhere in safety, and it's short and it's in a controllable place, and that would be cool. Okay, from there you go a distance, and this would be a long distance in my boat. This would be where it goes all the way up to the distribution panel, where the circuit breakers are. This would be where that goes to. And then there is a bus. Let me open this up. I bought these buses on Amazon a while ago. I like them. They've got great big lugs for the heavy stuff. They've got itty bitty lugs for the small stuff, because it's kind of a pain to find a terminal that goes over that great big thing that can go down to like 12 gauge wire. So this is all positively charged. It's protected at 200 amps. That's a lot of power. If this touched this, it would be a bad day. So on a boat, you want to have this securely bolted to a bulkhead and this securely bolted to another bulkhead. I like that these have these little covers. They don't make it impenetrable, but it makes it a lot easier to have a little armor, little insulated armor to protect things from happening. Okay. We're going to leave that now with a more reasonably sized wire that's going to my circuit breaker panel. I bought this used on eBay because it was cheap, and all I wanted it for was this demonstration. I thought these were actually switches. They're not. They're circuit breakers that are switchable, but they pop and then you push to reset. I wouldn't get this kind. I would get the kind that actually have a switch that you can turn off, and then they become dual duty. They're a circuit breaker if too much current is pulled in that circuit, but also you can just go click and turn them off and it's off. Right now on Temptress, I'm not there. All these switches are off except for the bilge pump. Let's take a look at the back of this. One side of all these circuit breakers is just connected together and positive. They did it with wires and jumpers and 1/4-inch spade connectors. If you use the kind with screw terminals, you can make yourself a copper strap that will go right down the whole line, and it's less messy, uses less space, and I think has a lot less resistance. And then the other side is your active side going to the circuit. So I have two circuits functioning here. One is bilge and one is accessory, because that's the closest I had here. Now these go to a lower amperage protection. So I think these are both 5 amps. 5 amps because this is smaller wire. if this wire was given 200 amps of flow through it, it would be a real problem. It would start wood on fire if it was near the wood, and it would probably melt on its own. So whenever you go from a bigger wire to a smaller wire, you have to have a circuit breaker to control that, a fuse or a circuit breaker. Okay, off this one goes. It goes to this switch. It goes to the bilge pump, and then back the shorter route to the ground side, and of course to the battery. Okay, I'm gonna turn this bilge pump on. I got this out of my shed. I think it's gonna scream for a second. It has bad bearings. Well, let's go. Okay, you can hear it screaming. Anyway, I have control of it just on and off. That's not how you should hook up a bilge pump. There's another circuit that goes to an automatic device that would say there's water in the bilge. Turn this on automatically. I have a whole video on how to wire a bilge pump, so I'm not going to go into detail on that. Just go to the other video. Now the other one goes off and about to, I would call that my lighting. And here's a light that I would put on the ceiling, and it has its own switch. So simple as that. That's it. That's how the wiring is in a DC system. There isn't much to it. Just the only real safety thing, I guess, would be have adequate wire. And when you go to a smaller set of wires, you have to have a circuit breaker of some kind that will stop the circuit if too much current were to flow, and too much is defined by what would make this hot. That other video where I go into that, I actually like melt a wire hooked directly to a battery, kind of like a flash bulb. It shocked me when I did it. We want to minimize the resistance, and we're going to do that by using big wire when we can, when it's practical, and we're going to minimize the length of the negative side. That's about it. Bye from Clark on Temptress.